Okay, good morning, everyone. I'm late because I'm having some trouble with Teams. For some reason, I cannot activate the Q&A for this session. But what I did in the meantime was activate another website. It's called TreeSider. You have the URL in there. You can join there and ask questions. You can also vote for someone else's question if you want to ask it yourself. And I will try to keep an eye on it. And if there's any question at any point, I will just go ahead and answer. So I will just leave that for a minute. You can just go there and post your questions. I'm actually thinking about changing how we do the live lectures because this is a little bit of a mess. And I would actually like to hear you, ask the question. But anyway, in the meantime, we can prepare everything here. We're going to start with the second lecture. And the second lecture is going to be the second part of the methods block of the course. So what we saw on Monday was everything about data-driven studies. So we talked about the variables, the relationships, what kind of relationships we look among variables. We talked about third variable problems, things about the confounding Larkin variables, Simpson's paradox, and then sources of variability and error. And we saw that we are always going to have some kind of systematic error if our measurements are not the best, and random error always because we study samples. So we're going to focus more today on this last part on samples. And we talked about everything from this perspective of a study. So we wanted to study a certain process, be artificial or natural, in which there are certain inputs and certain outputs. And how this process works is through several factors, or there are several factors that influence how the process works. And we saw that there are certain things that we can control as the experimenters. There are certain things that we cannot control, but we can nonetheless measure. And of course, there's plenty of things that we do not know and can potentially influence the process. So the whole idea was, how do these factors affect the response, the output here? So today we're going to talk a little bit about the measurement, the levels of measurement, how to build scales, then go with populations and samples, factorial designs, and what the factor is really and the effects of a certain factor. So this is going to be probably the hardest lecture of this block. So let's talk about measuring. So we saw is that we care about variables of different nature, and we typically differentiate between quantitative variables and qualitative measures. Quantitative are those that can take a numerical value. So you can think about age, a response time of a certain algorithm, a test score. Those are things for which a number makes sense. By its nature, this variable is a number. And then qualitative variables are those that do not have a numerical variable, or maybe they do have it, but it doesn't make any sense. It's just an arbitrary number. So you can think about the sex of a person, a programming language, a company. Those are variables that do not have a meaning from a numerical point of view. Again, sometimes they can be coded as a number, but the number is completely arbitrary. It doesn't mean anything. And of course, we have variables and we can aggregate them. We can compose them in different ways. We're going to talk a little bit about this later. So for example, we could have a variable called company size that aggregates multiple variables about the size of a company. So it could be, for example, the number of employees, the year that the company was founded, the number of departments, the age of the CIO, the sector, revenue, etc. So those are multiple variables that we could consider into aggregating a company size variable. But nonetheless, the important thing about a variable is that whenever we carry out a study, the levels of the variable, and that means the possible values, that's what we call the levels, should be both exhaustive and mutually exclusive. Let's take a look. So exhaustive means that the variable should include all possible levels of measurement. So if we have, for example, we're asking of the country of origin of a person, we should make sure that all the countries are available to select as an answer. There are going to be many cases in which there's going to be too many levels, too many possible answers. So it's always a good idea to include a certain other response levels that they can say it's none of the levels that you give me, it's just something else. So for example, when you ask about the education of a person, you can list multiple degrees, but of course, in some places there's something a little bit less popular, and it's going to be a certain degree, and you can just let the people tell them. What happens if you want to study a quantitative variable, something that in principle could have a very large number of levels? You can think of a number, a temperature. Then what we do is sample some values of that numerical variable. And the thing is that we have to be careful with both the bounds and linearity. So if you know your variable is bounded between two numbers, then you should be careful with making sure that in your study you include numbers close to the bounds, so that you know exactly what the behavior is around the bounds. And also you should think whether the effect of that variable is going to be linear or not. So should you sample levels of the variable throughout the entire domain, at equal spaced intervals, or should you pay more attention to low values because a lot of the observations are going to be in these low values? Sometimes we can put together certain levels, if, especially afterwards, we see that we don't have many observations of some levels. So, for example, something very typical here is the case in which we ask people for their age, and we give them intervals like 5 to 10, 10 to 15, 15 to 20, etc. And maybe sometimes you see after collecting the data that you didn't have enough persons from 5 to 10, then you can put that together with another interval 5 to 10 and 10 to 15, for example. It's fine to do that as long as you realize that you're making this margin. So this is what we mean by being exhaustive. You should account for all the possible values that the variable should have, and all those possible values, all those levels should be able to appear in your data. And then by mutually exclusive, we mean that only one level is possible. Only one answer, only one level, only one variable, one value is possible. The example that I always give is this one in the US. When I was living there for some time, and then I always found this completely stupid. So I'm from Spain, and according to the US, I'm a Spaniard. Okay, that means I should say I'm Hispanic, but I'm not, I'm Caucasian. So this is an example in which if you are from Spain, you are actually both of them, but they only give you the option of being Hispanic. So this is a case in which the variable, it's not mutually exclusive. So we have two different levels for people like me. So in these cases, you should try to think about options like check all that apply, or making many variables binary variables, so you can allow people to check all of them, and then instead of having just one variable, you have multiple variables. So you could have one variable for whether you're Hispanic or not, whether you're Caucasian or not, whether you're Asian or not, and maybe you can even think of hierarchies. So these would be cases in which one variable can turn into multiple variables because we have this problem of exclusiveness. And we have to be aware that a poor selection of the levels or poor wording may hide effects or may even introduce bias. So think, for example, a survey in which we ask people whether they are employed or unemployed. Think about people with multiple jobs, so people who do moonlighting. Maybe there is an effect in there. Maybe people who have multiple jobs are different in a certain way for the purposes of your study. But if you only ask this question, employed or unemployed, you're going to miss that effect. So it's probably a better idea to ask for the number of jobs. It's going to be more informative. And something that we also know that happens is just the words that we use to describe the levels of a variable may have a certain bias on people. So for example, we know that if you put in front of people video recordings of traffic accidents, and then you ask people to rate the accident as, being low or high, the damage, being low or high or low or brutal, then people are often going to choose high, but not so often going to choose brutal, because the connotation is a lot worse than high. So just by choosing one or another option, by asking people this option or this other option, we're going to have a certain bias in our results, because people tend to stay away from such extremes as brutal. So we have to be careful with how we choose the words we put into a survey, for example. And so this is about variables. They have to be, again, exhaustive. All possible values should be available and mutually exclusive. And then once we have the variables, we have to realize that they are measured in different levels. And we have what we call the 4 levels of measurement, or types of measurements. So if you measure one variable that is by nature qualitative, a categorical variable, that's what we call a nominal variable. So again, think about the sex of a person, man or woman. Think about the nationality, who or where are you from, which country, programming language. Those are just categories. There's no order between them. So one country is not coming before or another or after another country. Same with programming languages. There's no magnitude, no difference between them that you can quantify. Then if we go a little farther, we can have ordinal variables in which we do have an order, but not a magnitude. So we know that some things come before some other things, but there's no notion of distance between them. So for example, you can think about some variable measuring the difficulty of something. And if the possible levels are no difficulty, some difficulty, or much difficulty, we know there is this order between them. We know that none comes before some, comes before much, but we're not quantifying how much, how farther apart those levels are. So we're able to quantify this qualitative measurement of difficulty, but we cannot really put a number on it. We just know that one comes before the other. So we know that much is greater than none, for example. And then if we want to start quantifying differences, magnitudes between different levels of a variable, then we should attempt to have an interval variable. And in these cases, we do have a magnitude, but we don't have a notion of ratio. There's no zero, or the zero doesn't have any meaning. And in this kind of variables, we find, for example, the temperature. We're going to talk about it. We can find dates. So we know that between October the 2nd and October the 5th, there is a distance of 3 days. But we cannot say that October the 5th is twice as much as October the 2nd. That doesn't make sense. So there's no notion of ratio. Again, there is a notion of distance, of magnitude, but no ratio. Think about the age range. We know that the distance between 5 and 10 years old and the distance between 10 and 15 years old. We know we can quantify a distance in there, but not a ratio. And then if we have a variable in which the ratio does make sense, and does make sense because the value of 0 has a meaning, then we have a ratio variable. And in this case, we also have temperature. We're going to see why temperature is in both places. But you can think, for example, about a length. There is a notion of no length, of 0 millimeters, for example. And we know that 20 centimeters is twice as much as 10 centimeters, because the notion of 0 does have a specific meaning in this variable. Same thing for duration. 3 seconds is 3 times as much as 1 second. We can do things like that. We can have ratios. Or the mass. There is a notion of no mass, so we can quantify that. And this is important because the kind of operations that we can perform on our variables depend on which level we are measuring the variables. So whenever you design some study and you identify the variables that you want to measure, you have to realize at what level those measures are occurring in your study. Are they nominal, ordinal, interval, or ratio? So let me give you the example of the temperature. So we know that the temperature can be measured in multiple units. We have here Kelvin, Fahrenheit, and Celsius. And we know what the absolute zero means, right? This is absolute zero. that basically means something like no entropy, no heat. Then we can have, for example, 300 degrees, 450 degrees, 600 degrees. And we can here quantify the distances and ratios between them. So we know that from 300 to 450, there is a distance of 150, and we know it's 1.5 times. Same thing for the 600 is plus 300 degrees, and it's twice as much. These are numbers that make sense. These are operations that make sense in a Kelvin scale. Now, if we go for Fahrenheit or Celsius, the problem is that the 0 Celsius degrees does not have a meaning. It's just a completely arbitrary number. It corresponds to somewhere over here. And so we cannot compute ratios between Celsius variables. So, for example, here we have the correspondence. 300 Kelvin is 26.85 Celsius. 600 Kelvin is 326.85 Celsius. So yeah, there's distances between them and they correspond to the distances in the original scale. That's fine, but the ratios are different. So 326 degrees Celsius is not twice as much as 26.85. We know that. Or let me put it this way. If we say that there's out there 40 degrees Celsius, we cannot say that it's twice as hot as 20 degrees Celsius. That doesn't make sense because Celsius here is an interval variable and Kelvin is a ratio variable. Now this might seem stupid, but it's very important that we are aware of this because we can compute standard deviations and things like that from Kelvins, but not from Celsius. They don't make any sense. And that's why in the scientific literature, for example, even though the unit that everyone uses is the Kelvin, it's very frequent to see people reporting Kelvins in Celsius and distances in Celsius, intervals in Celsius, because the intervals are going to be the same numbers as in Kelvin. It's just the ratios that are different. And everyone understands Celsius better than they understand Kelvins. So this is the reason why we have to be careful about at which level we are measuring our variables, because there are certain things that we can do with them depending on the kind of variable that we have. And with a little bit of more detail, here we have a table. So for example, in a nominal scale, there's no such thing as multiplying or dividing, for example, countries or addition, or there's no order, nothing goes before or after. The only thing that we have is equality. Is one country the same as another? Yes or no? And then you see that the only one in which multiplications and divisions make sense is a ratio variable. So something like a standard deviation, it only makes sense in a ratio interval. A ratio variable. So think, for example, that you're running a survey or you're observing someone working and you ask them for the difficulty. You give them the option of saying none, little, some, or much. That's what people can tell you. Imagine that you observe over multiple subjects the results 1, 2, 3, 1, 2, 2, 0, 3. Should you use the mean or the median? Now, if you look at the level of measurement, this is probably a ordinal variable, so you should use the median. You cannot just compute the average, the mean score of these observations because it doesn't make any sense. Because these numbers 0, 1, 2, 3 are completely arbitrary. What people are answering to you is none, little, some, or much. There's just an order, but there is no magnitude between them. Any magnitude that we give to those numbers is completely arbitrary. So for example, you see here, what would have happened if we say 1, 2, 3, and 10? Then the 10 would be a lot more represented or would have a much larger weight into the computation. So that's why we have to be aware of these issues. So again, it's important that we know at which level we are measuring our variables because we cannot make all operations all the same. And then once we have multiple variables and we realize the level of measurement, we can start going a little bit farther. And we can talk about scales. So a scale is essentially an instrument that is going to allow us to assign a quantitative variable to something that by nature is qualitative and very difficult to measure. So think, for example, about self-esteem. How do you measure that? or intelligence. How do you measure that? So concepts that are difficult to measure, and it's going to be very difficult to put a number on them. How can we nonetheless try to quantify them in a numerical way? So the thing is they're going to bear some degree of subjectivity and should always be backed up by theory. That's not something that we're going to get into, but just be aware that whatever number you come up with or how you come up with that number should be somehow backed up by theory. And so the thing is that a scale is going to consist of several response items. So several questions to be answered individually, and then we come up with a final score from those questions. And we're going to cover two, Thurston and Likert scales. So how do we build one? So let's say that we want to build a scale for people to report self-esteem at work. So what is their self-esteem at their job? Then step number one would be we generate a set of potential scale items. So basically come up with statements. We can do it ourselves, or even better, get a bunch of people to do this for us. And those statements are not about what we believe our situation is, what we believe our self-esteem at work is, but what the possible answers are that people can give you. And again, building a scale is important because if you ask people about self-esteem at work, first, they don't really know. Second, they can't really put a number on it. Third, they're probably going to lie a little bit because no one wants to report that they don't have any self-esteem. So how can we put a number on that? Okay, we generate this potential set of scale items, and we come up with a list of 5, for example. So item 1 would be an answer that someone can give us. Let's say, I feel good about my work on the job. Item 2, I'm uncomfortable at work. Item 3, I feel like I make a useful contribution, etc., etc. So you come up with these possible answers. And then in step 2, what we did is we get a set of people, judge the items with respect to how much they favor the concept of interest. So how much does each of the 5 items favor the self-esteem at work? And then people can just give you numbers from 1 to 5, 1 to 7, 1 to 11, whatever you want. And it's, again, not about what they personally believe those items favor their own self-esteem, but how much they think that item in general would favor self-esteem at work. So again, let's say item 1 was, I feel good about my work on the job. That should be a positive correlation with self-esteem, right? Then we ask, let's say, a set of 4 people, and they said from 1 to 5, the scores are 4, 4, 3, 5. So this is what they think the magnitude is of correlation between that one statement, item 1, and self-esteem at work. Then for item 2, we see that numbers are quite low, 2, 2, 1, 3. Same for item 4. People gave 1, 1, 2, 2. Item 4 was, I can't handle my job without assistance. That has a negative connotation with respect to self-esteem. And people think it's quite bad. It's 1, 1, 2, 2. So we have these judgments by people. And then we have to come up with the final set of items and how much they're going to contribute. So in step 3, what we do is we get all the items and sort them by the median score. And so in our case, what we find is that item 1 is the one more positively correlated to self-esteem according to our judges, followed by item 3, item 5, item 2, and item 4. So we have here a sorted list of items in terms of how they favor the concept of interest. Then in step 4, what we do is we select a certain number of items that we want to ask people about. And the idea is that we more or less do it covering the full range. So we could do something like the first, the one in the middle, and the last one. And that way we are covering more or less the whole spectrum. And again, it's not just about blindly looking at the numbers, it's just about looking at the items and seeing that you're not basically asking the same question again. So you have to look a little bit into the details and make sure that that you're not making any mistakes. You shuffle the items, and then that's it. You have these 3 questions that you are going to ask someone when you want to quantify their self-esteem at work. So let's say that you go to the company and then you ask the question to all your employees, and you get the answers. How is it going to look like? Then is going to be this list of 3 questions, and people say whether they agree or disagree. They either agree with the statement or disagree. And now this is going to be for each of those subjects, each of those employees, their perception. So how much they agree with that statement. So let's say that we get one employee in particular, and that employee agrees with this statement, disagrees with the second one, and agrees with the third one, which, by the way, corresponds, as you see, to items 4, 5, and 1. How do we compute a subject score? So how do we quantify self-esteem based on the answers that the employee gave us? We have 2 options. We can just compute the mean scores of the items that they agree with. So, for example, the employee agreed with item 4, that's a score of 1.5, and also agreed with item 1, which is a score of 4. So we do 1.5 plus 4 times 2, that's the average, and we quantify the self-esteem of this employee at 2.75 in a scale from 1 to 5. And again, this is a way of coming up with a number, coming up with a way of quantifying something that, to begin with, is going to be very difficult to quantify, and we go with the process of coming up with these questions and values for the questions, such that by answering those questions, a person, an employee in this case, is going to give us the notion of self-esteem. Anyway, the second option that we could go with would be computing the fraction of items that the employee agrees with, knowing that sometimes you have to correct for direction. So, for example, item 4, if the user or the employee agrees with item 4, it's actually a negative connotation, so we have to kind of reverse it. So in this case, we could say that the employee only agrees in terms of positive items with item 1, so it would be 1 item over 3, 66%. That's how we quantify the, sorry, this is 33%, I'm figuring out. Okay. So again, this is a way to quantify something that in principle is very difficult to quantify and very subjective. This is a Thornton scale. If we go to a Likert scale, let me check the Q&As. Okay, we have a couple of questions. Let me just finish with the Likert scale and I'll go through the questions. So in a Likert scale, everything is going to be the same. We just start changing in step number 3, in which we select. So we had these judgments about how much these items favor the concept of self-esteem. And then what we can do is remove the items with a low item to total correlation. So the ones that are less consistent. And the idea is you compute the sum across columns. So what is the total score given by each of the 4 judges? So we sum these numbers and we get 13. We sum these numbers, we get 13. So each of the 4 judges, this is how much they gave. And the idea is to compute the correlation between each of the items and the total. So in this case, this is a 0.33. Item 4, we compute the correlation between this and the total, and it's a correlation of 0.94. And so the idea would be to remove the items that are least consistent with the total. So in our case, we would remove items 1 and 2. And only administer in the scale items 3, 4, and 5. Another option would be to remove those that have a low range of scores. So you can compute here the range of scores. I believe this is the interquartile range. And it would be just, for example, in this case, remove item 5 because it has the lowest score. So this is in order to select which items we are actually going to ask about. How do we ask about them? Then what we do is offer this ordinal scale. So we say for each of the items, do you strongly disagree, for example, disagree, neutral, agree, or strongly agree? In this case, we have 5 possible answers. There could be 7 possible answers, 3, it's up to you. But in this case, let's say that we have 5. And so we go to the employee, we gave them this set of 4 questions, and then we let them answer. And in this case, this is what the employee said. Disagree with the first statement, strongly disagree with the second one, neutral the third, agree with the fourth. How do we compute a final score of self-esteem for this one worker? Then what we do is we sum the scores of all the items. Knowing that, again, we might have to reverse the score for some of them. So for example, item 2 is actually a negative statement. This is negatively correlated, so we have to reverse it. So in this case, the user or the employee gave us a disagree. This would be a score of 2. Once we reverse it, it would be a score of 4. So what we have is 4 for that item, 5 because we also have to reverse this one, 3 and 4, 3 and 4, and the total score is 16. So in this case, we quantify the self-esteem of this employee as 16 over 20. So this is what the Likert scale is, and in general, this is what scales are. If you think about concepts that are going to be very difficult to measure, and of course this applies a lot to concepts that involve people, subjectivity in some degree. This is why we build scales, to try to quantify something that is very hard to quantify. And if you use numerical scales, it's often a good idea to use positive and negative numbers to suggest agreement or disagreement. So for example, instead of saying disagree is 1 and agree is 2, you could say -1 and 1 to have this connotation that negative means something, well, negative, something bad, and the positive number is something good. Sometimes it's worth it to discuss whether you should include a neutral response, because what we say is that sometimes people just say neutral when they don't know. It's not that they don't have any positive or negative feeling, it's that they just don't know. And of course, we have to try to avoid problems with the wording, the endpoints, the labels, etc., etc. So think about the difference that you might have. How might you bias the results? If you ask people whether they strongly disagree a lot, or very much disagree, do you think people can give you different answers depending on how you ask? And then, by the way, something that we see a lot is that in many surveys, we see questions that resemble a scale item. So for example, does corruption hamper economic development? And then you can answer strongly disagree, etc., etc. A lot of people confound this with Likert scales, but this is not a scale. This is just one single item in which the scale of measurement resembles a Likert scale, but this is not a scale because it's only one item, only one question. And to see why this is important, this is actually a study from not long ago. And what we saw is that they had all these different words for measuring goodness, so to speak. So something can be abysmal, appalling, dreadful, terrible, very bad, average, mediocre, not bad, somewhat good, etc., etc., all the way up to perfect. And what they ask people is to give a number between 1 and 10. So for you, what does each of these words mean? What number do you think this number means? What number do you think this word means? And over here we have the distributions, so what people gave, and here we have the averages. So the one to which people give the highest scores, the one that people think have the largest positive value, is perfect. When you tell someone that something is perfect, they on average give a score between 9 something. Between 1 and 10, they say it's 9 something. The worst of all is abysmal, in which people give a score of about 1.21. And in between, there's a huge overlap. So you see, when you're trying to develop a scale and you're thinking about what words should I use to connote different levels of goodness, you can think about a scale like this. So how people think about these words. And if you want to do a scale from 1 to 5, for example, you could say this is going to be 1, this is going to be 5, and then in between you have 2, 3, 4 maybe, and you can use some word from there. And the interesting thing is that they did the same thing between people from the US and from the UK, and there was some disagreement, like in this case, but for the most part, they tend to have the same order. The numbers change a little bit, so it looks like people from the US are a little bit more optimistic towards here, but a little bit pessimistic over there. But in general, we see this order kind of remains the same. Okay, and to finalize, we have indexes. So indexes are just a way to combine multiple variables into just one. So if you can think, for example, how can we come up with a number to quantify the happiness of citizens in a country? Then you can think about all the possible factors that might affect the happiness of a citizen. And you could think, for example, of an economic index. We know that if people have debt, that's going to contribute negatively to their happiness. If they have a large income, that's going to contribute positively. Purchasing power. You can think about the physical index, life expectancy, cancer incidence, social index, divorce rate, crime rate, lawsuit rate. So you can think about all these factors that might have a positive or negative correlation with happiness index, and then you find certain ways to combine all these scores into just one, so that you can compute a happiness index, a number to quantify happiness. And then which rules you use, of course, this has to be backed up by some theory. So somehow you have to say, or you have to argue why, I don't know, traffic has twice as much impact as noise in the happiness of people. If there's something that you can quantify, fine. If not, you have to argue why you're giving it twice as much weight. And there's plenty of indexes around there. Probably the most famous one is the Gini index, which measures the inequality, economical inequality in people. All right, so all in all, this thing about measurement goes in the direction of having construct validity in our study, what we talked about on Monday. And construct validity essentially means, are you really measuring the variables that you want to measure for whatever hypothesis you want to answer, or for whatever thing it is that you want to study? So we have to be very careful in thinking about how we measure the concepts of interest. And usually there's not going to be one variable directly corresponding to the concept that we want to measure. We have to go around it. And for example, we can develop several variables. We can come up with indexes, scales, etc. And whatever we measure, we have to be really sure that it's measuring somehow the concept of interest. In many areas, especially if you work with people and you go to psychology and social sciences, there's going to be instruments already there for you. There's plenty of scales. There are scales for effort, for example. And you have to go through the literature and try to find how do people measure a certain concept I'm interested in. Again, this is particularly important if your study involves people. And to give you just an example of how things can go wrong, this is from a paper, I'm going to say like 5-6 years ago. People in Princeton said that nobody would use Facebook by 2021, so next year. Why did they make that claim? Because they were looking at numbers. So how often do people look for Facebook on Google? And here we have the date, and how often people look for Google, or sorry, for Facebook on the internet. They did the same thing for MySpace, which maybe most of you don't know, but it was a social network also that was quite popular a few years ago. And it kind of disappeared around 2012. Around here, MySpace closed. And so they thought, hey, if this happened with MySpace and we see something similar happening with Facebook, we are going to extrapolate and say that by 2021, no one's going to use Facebook because we have this one variable that measures, let's say, how healthy the social network is, which is how often people look for it on Google. That's the way that they chose to measure the health of a social network, or how active it is, how often people look for it on Google. And then, of course, the people from Facebook replied saying, that's nonsense, because here you have our number of users and it's just going up and up and up and like crazy. We actually have more and more people. So actually this study doesn't make any sense. And of course, they did their own study and they predicted that no one would be in Princeton by 2021. So what did they do? Same thing. So how often do people look for Princeton in Google? And same thing for all the other universities. So what they measure is here how often people look for a university, and here they measure the number of students in that university. So each of these points corresponds to one university. They saw there is this positive correlation, and they also measured how often do people look for Princeton on Google, and they saw that it was decreasing. And if you extrapolate, more or less, assuming this is correct, they predicted that by 2021 there will be no student in Princeton. They know that this is wrong, but they're just making fun of the guys from Princeton for using an obviously wrong variable to measure something that is not really correlated with what they want to measure. So this is a problem of constant validity. It's a very fun one because, hey, it's Princeton, right? And it's Facebook, and these kind of things happen. Anyway, so this was the part about measuring. Let me see the questions. We have a couple of them. Is there already some info available on the exercises and when we can start on them? I'm going to post the full schedule today. There's going to be exercises in 5 weeks, but not this week. So don't worry, there's nothing to submit this week or the coming week. Again, the full schedule is going to be posted today. And add ratio and interval variables, scale variables of SPSS. I don't know SPSS, so I'm afraid I cannot answer that question. I can try to look it up. Anyway, I think we can have a break around here, and we come back in 10 minutes, so 20 to 12, and then we continue with sampling. So let's stop here, 10 minutes, 20 to 12, and we continue. Again, if you have any question, post it online. Let me open here. You can go there and post your questions. See you in 10 minutes. All right, we're back. Let me go to the Thorsten scale again, because we have a question. So the question is, item I learned from my colleagues, so item 5, is incorporated into the scale. The answer is neutral, so it doesn't have a certain direction. So why is it included if it doesn't have a direction? Well, that is completely subjective. Whether it has a direction or not, it's not up to us. It's up to this panel of judges, of people who judge how they correlates. So in this case, in a scale from 1 to 5, this set of 4 judges, they said that the concept, the self-esteem at work, correlates in, they give a rate of 3, 3, 3, and 4. So for them, this is kind of neutral, 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 and a little bit positive correlated with the self-esteem. This is just what they said. So they agree, they disagree. This is the point. So the thing is, when you include all the items, you should try and have more or less something that covers the whole thing. If you're looking for 3 items, then you do those. So in a scale from 1 to 5, you should try to include more or less everything in here. So if you want to have a final scale with 7 items, then you choose somewhere around here, around there, 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 right? So you try to have 7, more or less equally spaced. That's why item 5 in this case came up in the final scale, because it was just judged as a 3 on average. This is why this is again a little bit subjective. And hey, if it gives a 3, it's a 3. That's what people think it is. Okay, so let's start with sampling. Let's actually start with 2 common fallacies. The first one is called ecological fallacy. Let's say that we have this classroom, and we know that the students in the class are very good at math. If you claim that Bob, who's a student from class A, must be good at math, this is a fallacy. So just because the group in itself appears to be good at math, that doesn't mean that all the individuals of the group are also good at math. This is what we call the ecological fallacy. We have kind of the opposite, the exception fallacy. So if we know that Alice and Bob are very tall and they're Italian, we cannot claim logically that all Italians must be very tall, because we are generalizing based on only these 2 observations. So we cannot say that all the group of Italians are very tall because we observe 2 of them who are. And therefore, by extension, if we know that the average score in a class is a 4, then we cannot say that there must be many students with a score of 5 or 4. We know that that is the average, but it could be something very different. So imagine that you visualize from 1 to 10, you could have all 4s, or you could have many numbers there, and a few there, and the average be 4. So we know all these are fallacies. They cannot logically follow from what we know. And the point is, we need to look at the distributions. If we want to make statements about these variables, we need to look at the distributions. You know what a distribution is, right? So it's basically a function that assigns a probability to every possible outcome of a random experiment. So in this case, the random experiment would be selecting a student from the course, from the class. So let's say that we sample 1 student randomly, and that student turns to be Bob, and it turns out that Bob has a score over there. Then yeah, the classroom in general was kind of good at math. They had an average score of about an 8, but actually Bob was doing quite bad in the score in the test. Yeah, Bob has a very low score, so we cannot say that Bob is also good at math. It could be a case like this, very simple. So again, we need to look at the full distributions before we start making claims about a variable. And we're usually interested in the mean scores, in the mean average. So what is the average score of the test in the class, for example? And this is important because the variables that we are interested in, they have a certain distribution in the population that we are interested in. So let's say that what I want to measure is the height of the people in the Netherlands. Then my population is the citizens of the Netherlands, all the millions of citizens in the Netherlands. The variable I'm interested in is the height of people. Now, those two together define a probability distribution. So we know there is a certain distribution of height in the Netherlands. That's what I want to find out. And maybe I'm more interested or particularly interested in the mean and the standard deviation, for example. If I want to estimate that, I want to measure that in my study, then there's a problem. Normally, you do not have access to the millions and millions of citizens in the country. You just don't. So you have to make a sample. So randomly choose a set of people. The more the better, we know that. Such that we measure the variable on that sample of people, and then we try to generalize the results to the whole population. So that's what we typically do in all studies, because we do not have access to the full population, because there are too many, because they don't exist anymore, or they don't exist yet, because they're too far away or inaccessible to us. There's many reasons why we don't study the full population, why we don't measure the variables on the full population. We had to resort to a sample. And so the question is, how do we sample? And what is the effect of sampling? So let's say that I'm interested in measuring the days to recover of a certain surgical procedure. So say we have a new surgical procedure, we operate on people, and we're interested in knowing, how often or how long does it take patients to recover. Now let's imagine that in a hypothetical world, we were able to know the distribution of that variable for the full population of patients, for absolutely everyone. And let's pretend, just for this lecture, that the true distribution looks something like this. So we have the days to recover. This is the distribution in the full population. And let's say that the average, we call it mu, is over there. So a little less than 1 day. Okay, that is what we want to know. If we were able to operate on all people and then measure, we would know this population. But of course, we cannot do that. We have to resort to a sample of patients that we might have in the hospital. So what is the average recovery time mu? That's what we want to find out, the true value in the population. The study will go something like this. We draw a sample of patients and compute the mean score in the sample. So on average, how long did it take for the patients to recover? And then what we do is we estimate mu with this sample. If you remember X bar, this is the sample mean. And what we do is we do this. We say that the estimate of mu, that's what the hat means. When we have a hat, that means we're estimating this statistic, the mu. So in this case, we say the estimate of the population mean is going to be the sample mean. We use the mean observed in the sample as a way to estimate the mean in the population. And the question is, well, of course, different samples are going to produce slightly different results. If you get the patients in one hospital and compute the sample, you might get a slightly different result, from a different hospital, from the patients in a different hospital or a different country. So the point is, because you're sampling and you cannot study the full population here, you can only study a sample, you are going to have a certain degree of random error. So linking back to the previous lecture, this is where the random error comes from. In practice, we only have one sample. We only have one sample of patients in this case. So how can we quantify the random error? We don't know anything about the true population. That's what we want to find out in the first place. And if we only have one sample, how can we quantify this? We're going to talk about it. So let's say that we go to a hospital and we have a sample of 30 patients, and this is what we observe. In red, we have the true value, the true mean days to recover in the population, the full population, and in blue, we have the estimate. So for example, this particular sample would be overestimating the true value by a little bit, because the blue one is to the right of the red one. Let's say that we go to a different hospital, and of course, we're going to have a slightly different distribution. In this case, they're very, very, very close together. We may go to a third hospital, we get the patients in there, we measure, and in this case, we are slightly underestimating the true value. Again, we don't know what the true value is. That's the point. What I'm trying to show here is that depending on which specific sample you have, you might be to the left or to the right, a lot to the left, a lot to the right, or just somewhere around the mean. And if we sampled, let's say 100 patients, let's say that we go to a very large hospital and we get 100 patients, it turns out that we found something that was very, very close to the true value. So this is already a hint into the direction we have to go. Increasing the sample size, we are going to reduce the random error. So let me give you a little bit more intuition. Let's say that we are measuring the performance of a certain algorithm. It's measured between 0 and 1. And imagine that we were able to measure the performance on the full population, and the mean score is over there, about 0.30 something. If we get a sample of only 10 items from the full population, and we measure the variable, performance in this case, let's say that we end up here. This would be the estimate, the sample mean would be over there, slightly underestimating. If we get a different sample, we might be overestimating. We get a different sample, we are again underestimating, and you see that it's by quite a lot because we only have 10 observations. If we go and sample, let's say 30, then the distribution, the empirical distribution is going to look a little bit more like the true distribution. And the point is that if you replicate your study, you get 30 observations and then a different 30 observations and then a different 30 observations. You see that, of course, there's a certain variation. You are never right on the money. You never have the true value, but you get closer to it. And if we go even farther and always sample 100 observations, then we see that we are closer and closer to the mean, closer and closer to the mean. On average, we are expected to be closer to the true value if we have more data points, if our sample size is larger. And all this goes into the direction of the sampling distribution of the statistic and the standard error. So let's say that in this case, again, we want to estimate the mean performance, the mean mu in the distribution. That's our research question. That's what we want to find out, how large it is. And then what we do in an experiment is typically we make a random sample of a certain size, let's call it n, and compute the sample mean, x bar. Now, what we call the sampling distribution of x bar of the sample mean is the distribution of this sample mean over replications of the experiment. So let's say that n equals 10. What is the distribution of the sample mean over replications of the experiment of sampling 10 items and then computing the mean? Another 10 items and then the mean. Another 10 items and then the mean. So let me actually paint it here. Imagine that we have n equal 10. We sample 10 observations, and from here we compute the mean. We replicate the study. We sample a different 10 observations, and from there we compute the mean. We do the same thing, different 10 observations, compute the mean. And these are all replications. Now you can do this as many times as you want. And the question is, what is the distribution of these sample means? How much is this distribution going to change? And then this is called the sampling distribution of x bar. And of course, you can visualize it. So what do we expect the sample mean to be across replications of your study? And why is this important? Because if we have a sampling distribution that is very wide, then that means we have a lot of random error for any one given instantiation of our experiment, of our study. There's going to be a lot of variation in terms of where the sample mean is going to be around. If we see that the distribution is very narrow, that's good. That means we are not going to have so much random error because for any given replication of our experiment, we are going to be around the true value, close to the true value. So this is what the sampling distribution is telling us. How much are we expected to vary across replications of our study? And so the key point in the sampling distribution is the sample size. The more data you have, then the sampling distribution is going to be narrower. So here on the right, we have what is the sampling distribution for the mean score. And what we see is that if we have a very small sample size, let's say the dark green, we have this distribution. So the sample mean is expected to vary quite a lot across replications of your study. So for any one given study, you are expected to be way off the true value. If you keep increasing, let's say to maybe 100 observations, then that means your study is going to have more data. You're going to sample more observations, and that means the sampling distribution is expected to be something like that. So for any given replication of your experiment, you are expected to be closer on average to the true value. You are going to have less random error. And this is the whole idea of the sample size. It's about decreasing the random error that, hey, in any case, is always going to be in there. We know this because we are sampling from a population. And therefore, there's always going to be a random error. The point is, how large is it going to be and how can we minimize it? The way to minimize it is by increasing the sample size. So this is the idea of the sampling distribution of basically any statistic of interest from your data. It's the distribution over replications of your experiment. And then we have the concept of standard error, which is the standard deviation of that distribution. So if you have a high standard error, that means you have a high degree of random error. Your statistic is expected to vary quite a lot. If you have a small standard error, that means your statistic is not expected to vary too much. So for any given quantification we have of certain things in our sample, we can always compute a standard error, and that is going to tell us how much we can trust that number, how much variation are we expected to have in that number if we were to replicate our experiment. If we have a low standard error, that's good. I see a question. This is not about the lecture, okay? I will answer all these questions later. Okay, so this is the sampling distribution and the standard error. So let's say that I want to study again the height of the population in the Netherlands. That's what we call the target population, every single citizen. Now, for practical purposes, you never have access to all of them, even for legal reasons. For example, I work a lot on things about computers and music, and we cannot have access to all the music we want because of copyright issues, royalties, and everything. So yeah, our research, we would like it to be about all music, but it cannot be because we don't have access to it, plain and simple. So we have the concept of accessible population or the sampling frame. So what is the subset of this target population that we actually do have access to? So let's say that in my case, it's only the people within the university, only students. And then from there, we draw our sample. We randomly sample, in this case, students. So here's where I study, and I measure whatever it is that I want to measure. And then by doing that, I do a statistical inference of what I expect these variables to be in the sampling frame. So again, it would be something like here we would have mu, and here we would have the sample mean. And we're trying to make inferences about what that mu is in the sampling frame. This is what reliability is about how well or how close are we to this mu given the sample. And then we have to consider that we are generalizing the results from here to the population that we really want to target in the first place. And that's where we start talking about external validity. So how well can we extrapolate or generalize our results to other populations? And why is this important? Because this target population and the population that you actually have access to are normally different. Or what if I want to extrapolate this to, I don't know, Spain? Can we just generalize this number back to Spain? We know we can't. Actually, the Dutch are the tallest in the world. But this is a little bit of the idea of the target population. From there, we only have access to the sampling frame, and from there we sample. We study the sample, make inferences back. We talk about populations here, and then here it's a qualitative assessment of whether you can generalize or not. So how well do these sampling frames correspond to the target populations? And then we have to determine how do we sample. So how do we go there? How do we determine who is going to be in our sample? There's many strategies, and the important thing to remember is that they have to be the samples representative and large enough. Representative of the populations that we want so that we have external validity, and large enough to minimize the random error to a certain point. And this is important because all the results, all our conclusions are going to be restricted by how we draw samples. So how can we do it? The simplest one is what we call simple random sample. You simply just randomly pick people or pick students or pick songs or whatever it is that you're measuring, whatever your population is. And by the way, it's not always that straightforward. So you can think, for example, about selecting random IDs, like random student numbers, or selecting random phone numbers. This was something that used to happen decades ago. They would just call people to their homes to run some surveys, and they were just randomly picking up numbers from the phone book. Now, the problem is, if you call on a Wednesday to someone and they answer the phone in their home, there's a very clear bias towards people who are unemployed. So apparently the sampling process is random because you're randomly choosing numbers, but the people that correspond to those numbers are not a random sample. In this case, there would be a bias towards unemployed people. So it's not always that straightforward and something that you have to give a second thought. Then we have stratified random sampling, which is going to allow us to ensure that all groups of the population are going to be represented. So imagine that we are going to sample again all citizens in the country. Now, you could, for example, sample the same number of people in each city, because we know if we randomly choose people in the Netherlands, there's going to be a lot of people from Amsterdam, a lot of people from Rotterdam, from Utrecht, from The Hague, etc. If you want to make sure that you represent everyone in the country, what you can try to do is sample a number of people from each city, so that you know that you are representing all cities, even cities without a lot of population. And then it's about, when you analyze the data, to give a different weight to all these people. But in this case, we make sure that we represent the full population in a certain way. We also have something called cluster random sampling. And the idea is that you go to different clusters, or the population can be divided in clusters, and then you go to one cluster and study all the elements in the cluster. So for example, imagine that you go to one building, and then once you are in the building, then you ask everyone, or you run the study on everyone in that building. So the cluster in this case would be the building. Or you go to one city and measure everyone in that city. That would be a cluster. And finally, we have something called convenience sampling, in which we just sample people who are close to us, friends, co-workers, neighbors, students, things like that. They're not the best, because then you get into questions of how well they represent the population that you are targeting, but it's convenient. So sometimes this is kind of fine, because you don't expect your friends to be different from other people in terms of something specifically that you're measuring. Sometimes this is okay, sometimes it's not. And I want to finish sampling with two common misunderstandings. One of them is this idea that a random sample is always representative. This is not true, because if you think about it, every single possible sample of size n, if you think of all the possible combinations of n elements from the population, all of them are going to be equally likely to be drawn in a sample. Even those that are extremely, extremely infrequent, even the weird items, or even the rare items, those are going to be in a number of samples. And the idea is, again, you only have one sample. You don't know anything about the population. You only know something about your sample. There's no guarantee that your sample is representative. And the idea is that this is expected to be representative over replications of your experiment. So what this means is that if you replicate your study multiple times, you are expected, on average, to have a representative sample. But any one given sample is not guaranteed to be representative. And this is why we replicate studies over and over again, because Every study is just one sample. There's absolutely no guarantee about that one sample being representative. So what I recommend is always check the characteristics of your sample if you can, see that there's nothing strange, and replicate your study if you or others can. Always try to replicate your study. And hey, in science, we never take something for granted unless it's replicated a number of times. And the other one is this magic number of 30. There's a lot of people saying, you know, how many people do I need, or how many whatever is it that I'm studying do I need? And the magic answer is somehow 30. And this is incorrect. 30 is just a number where we have something happening in terms of statistics, but that's really not the answer to the problem. It depends on what is the minimum effect size that you want to detect. So if we are talking, for example, about days to recover of two different surgical procedures, it's about what is the difference that you would like to detect. Is a difference of 1 day enough, or are you aiming for something in terms of hours or in terms of weeks? Then depending on that resolution, so to speak, you are going to need more or less data. It also depends on the variability of the phenomena to begin with. So how much variability do we have in these days to recover in the first place? And then what we typically do is run a preliminary study and do something called power analysis. We're going to talk about it in the next lecture. And always search in the literature for characteristics of your populations. So you might be able to figure out that, I don't know, the standard deviation of the height of people is whatever. And then knowing that, you can aim for a specific sample size. So it's always dependent on what you want to detect and the properties of that thing you want to detect. We're going to talk about it later. So let me reiterate. If you ask at any time, how many do I need? And someone just give you a number like 30, 50, or 1,000, they're lying to you. Plain and simple. The correct answer is always, it depends. We're going to see in the next lecture how to actually compute this. It's always, it depends. So that was about sampling. And the last thing that we have to talk about is a little bit of experimental design. Let me check the questions. Nothing. Okay, so I'll just continue. So I want to talk a little bit about experimental design. Why? Because whenever someone was running some kind of study, you know, this used to happen a lot in agriculture. They were running experiments in agriculture all the time to see what was the optimal condition to grow some plants. But it can be anything. If you're trying to see the example that we talked about, coffee, the quality of coffee depending on the brand, on the pressure, temperature, quality of the water, brewing machine, etc. The point was, if you want to make a study like that, it used to be very common years ago, like 100 years ago, to vary one factor at a time. So you do one measurement, and then you change only one of the factors at the time and make another measurement, another observation. And then you change another factor, only one, and make another measurement. And all the time compare two measurements that differ only in one factor. Of course, this was highly inefficient and it required many experimental runs, and it was kind of constrained. The kind of things that you can compare, they are kind of constrained by how you run the experiment. But then in the 1920s, we had the development of what we call factorial designs. And altogether, the whole field of statistics experimental design was kind of reinvented in the 1920s. And one of the most important tools that we get out of it are, again, factorial designs and analysis of variance. So the principal idea is that we can vary multiple factors from time to time, from observation to observation, as long as we meet certain requirements. We're going to see what they are. And this led to very great developments in statistical theory and in general in science, in how we do experiments in science. So what are factorial designs? So remember what we talked about. We were describing our studies in terms of functions. So we said the dependent variable was some function or it depended on a set of independent variables, right? And all the time we're interested in knowing what is the effect of these independent variables on the dependent variables on the response. Now it's important to realize that each of those factors may have an effect or may affect the response at different levels. And we differentiate between the main effect and the interaction effect. The main effect of a factor is that is due to variations in the factor. So let me give you here an example. Imagine that I work in Bol.com or in Amazon, and I have this new advertisement campaign, and I'm going to communicate with my customers through email or phone. So factor one here is the channel, communication channel, and there are two possible levels, email or phone. And then I have another factor, factor two, which is the length of the message. Is it going to be a short or a long message? And then my response, my dependent variable is the purchases. Okay, so the main effect of the channel would be what is the difference in the response between email and phone. The main effect of the length would be the difference in the response in purchases between short and long messages. That's what we call the main effect. What is the difference in the response across the levels of the factor? And then the interaction effect are effects that are due to covariations with multiple factors. So what is the difference between combinations of the two factors? Are there differences between the combinations of the two? Yes or no? Let me give you an example. So let's say that this is sorted from low purchases to high purchases. And let's assume that all the studies already carried out, everything is nice, and we have email short, they're around here in terms of purchases, email long, they're around here. So for email, we would say that on average, we are about here. If we look at the phone short is around there, phone long is about there. So on average, we're going to say that the phone is also over there. The purchases in the level phone are about the same as the purchases in the level email. So what we see is that in terms of purchases, there appears to be no difference between email and phone. On average, they appear to lead to the same amount of purchases. So this would be no main effect of the channel, because for both email and phone, we have the same average purchases. What about the length? Well, for the length, we have short is over there and there. So on average, we're going to say that it's around there. And for long, we have on average somewhere around there. Now, we do see a difference between short and long messages. Long messages appear to lead to a higher degree of purchases. So there is a main effect here of the length factor, because purchases for long are higher than purchases for short. There is a main effect. Is there a main effect of the interaction? And that would be looking at differences across combinations in here. And the answer would be yes. And specifically, you get a very different answer with the email, depending on whether you are short or a long email. If you're a long email, you have the highest. If you're a short email, you have the lowest. So there is an interaction effect. The effect of the email depends on the level of the length. Long emails are different from short emails in terms of the purchases. So this is what we mean by an interaction effect and a main effect. Let me give you another example. So let's say that here we have the length and here we have the channel. So in this case, we see that short messages on average are around there. Long messages on average are around there. They seem to be the same. This over here is the response, by the way. So on average, the difference between short and long seems to be 0. So there's no main effect of the length here. Now, on average, the email is around there, and on average, the phone is around there. So there is a main effect of the channel. And there is no interaction effect because basically the lines are parallel. So there is not one specific combination that is differing from the others. So there is no interaction here. And this is actually what we see there. Here we have another example in which the average for the short is around there, for the long is around there, for email is around here, and for the phone is also around there. So there's no main effect of the length because short and long are around the same. There's no main effect of the channel because email and phone are around the same, but there is an interaction effect because the lines are crossing essentially. So we have specific combinations that are different from their average use. So we would have an interaction effect there. And here you can see all possible combinations of whether we have a main effect or not of each of the two factors and whether we have an interaction effect depending on what we observe in the data. I strongly suggest you to just go to the slides and try to figure this out yourself. So in which cases do we have a main effect and in which cases do we have interactions? And so these factors have different effects. They can have an effect at the main level or at the interaction level. And of course, we can have interactions between three factors. The other differentiation we have is that the factors can be crossed or can be nested. Crossed, it means that the levels of the first factor co-occur with the levels of the second factor all the time. Whereas in a nested factors, we have the levels of the first factor co-occur with only one level of the second factor. So let me give you an example, and it's going to be more clear. Imagine that we are studying the scores of students on tests graded by teachers. If we have every student tested on all n tests, so every student has to take every test, this is what we call a crossed design, because all the levels of the first factor, the student, are crossed or are measured with all the levels of the second factor, which is the test. If, for example, we have every student test, so every test being rated by a different teacher, that would be a nested factor. So the teacher would be nested within the test. So let's say that we have 10 teachers and we have 4 tests. Then the idea, four teachers per test. The idea would be that for test 1, we have 4 different teachers. For test 2, we have 4 different teachers. For test 3, we have 4 different teachers out of the 10. So here the teacher factor is nested within the test factor. It's not crossed because which 4 specifically are going to be different across different tests. This is what we call a nested factor. Teacher is nested within the test. And this is important because how we analyze the data is going to depend on things like this, whether we are looking at main effects or interaction effects. And in general, it's all about coming up with a model that allows us to analyze the data in a way that we can estimate all the effects of interest. And then once we identify that, what factors are we interested in and what effects are we interested in, then we have to come up with a study plan with an experimental design that allows us to estimate them, because it's not just about collecting data, it's about collecting the right data. So imagine that in the case of Bol.com, or communicating with the clients, maybe we are interested in seeing whether there is an interaction effect between the channel and the length. So we could have different analysis models. We could say, yeah, conceptually, the purchases depend on the channel, on the length, and whether we are personalizing to each customer or not. By the time we analyze the data, we might think about a model in which we have the main effect of the channel, the main effect of the length, the main effect of whether we personalize or not, and of course, random error. Or maybe we are not interested in personalization, but we are interested in the interaction between the channel and the length, because we think there's going to be a difference, depending on which combination specifically we have. And we assume there's no difference of personalization. That would be a different analysis model. Or maybe we already know that there's no interaction between the channel and the length, and we are just interested in measuring what is the main effect of the channel and what is the main effect of the length. Now, each of these is going to lead to a different study plan, to a different number of observations. Because, for example, for this one, we are going to need more observations than for that one. It's just a fact, and we're going to see why this is the case. So it's very important to first think about what you want to measure, then what effects you're going to be interested in, main effects, interactions, etc. And then afterwards, you come up with a plan, not the other way around. So what effects you're going to be able to estimate depends on how you collected the data. And so this goes to factorial designs. A full factorial design is one in which we study all the possible combinations of all the levels of all the factors. So imagine that we have a study in which we want to study two factors, factor A and factor B. Let's imagine that each of them has only two levels, so they are binary. The full factorial design would be something like this. So we measure the response for all the four possible combinations of the factors. So let's say this is email, this is phone, this is short, and this is long. We study all four possible combinations. Now, the thing about the factorial designs is that they are going to allow us to estimate all the main effects and all the interactions. We're going to be able to estimate absolutely everything, whether there are differences across channels, across lengths, and their interactions. Now, you can imagine that as we start adding more and more factors, and the factors are more and more complicated, this table is going to grow a lot. So there are many cases in which we cannot afford to run a full factorial study because it's going to be too expensive. And that's why we have fractional designs. And the idea is essentially that out of the full design of a full factorial design, we only run a specific combination of the factors. We only run a portion of the full design study. And so every time we cannot afford the full thing, we can run a fraction of it. There are standard studies, standard designs with desired properties. I'm not going to get into them, but just know that it's more efficient. So we do not need to run the whole thing. We can run only a few instances. The problem is that there's going to be some degree of confounding, what we talked about last week. And if you remember, confounding means that if two variables are confounded, two factors are confounded, we cannot really differentiate between the effect of one or the other on the response. And it doesn't matter how large your study is. If two variables are confounded, you do not know which of them is really related to the response. There's no way of knowing that. And let me give you an example. So let's say we have this full factorial design for two factors. This is what we saw earlier. This is going to allow us to estimate absolutely everything. Let's say that this is too expensive. I cannot afford to run four observations of this study, so I'm only going to run these two. And the two are factor A equals 0, factor B equals 0, factor A equal 1, factor B equal 1. The problem with this one is if we observe a difference between y1 and y2, we observe a difference in the response. There's no way of knowing whether that difference comes between the difference in factor A or the difference in factor B. So there's no way of knowing whether that difference is because of difference between email and phone, or whether it's because of difference between short and long messages. We can't. So this is a fractional design because it's only running a fraction of the full thing. But in this case, the main effects of A and B are confounded with each other. Whatever difference we observe in there, we don't know if it's because of factor A or because of factor B. A and B are confounded in this case. So this is the problem. Now, the idea is you get a fractional design that allows you to estimate the effects that you are interested in. So main effects are confounded with interactions, but not with one another. That is something that we can find, for example, in this table here. The problem in this table is that, yeah, we could see the differences between A, B, and C, but if we notice, let's say here, if we observe a difference in those two, we don't know if it's because of factor B or factor C. It could be the two of them. We could try and solve. So for example, over here again, we have, well, actually, let me clear it up. If we observe a difference between this and this, so the difference between factor A equals 0 or 1, we don't know if it's because of that or if it's because of this. There's no way of knowing that. Now we could say you can try and change this part, and yes, that resolves that problem, but then we have confounded between B and C. So what I'm going is, it's really non-trivial to come up with a design that allows you to minimize the confounding of factors. That's why we have standard designs. And the more effects you are going to want to study, to look at, the larger your study is going to have, the larger the sample size you're going to need. And the idea is that this all goes in the direction of the design resolution. So what is the resolution of a certain experimental design? So what you have to look for is a certain degree of resolution. So let's say a design of resolution 2 is one in which all the main effects are confounded with each other. So this is basically useless. If I observe a difference in the response, there's no way for me to know which of the factors is responsible for that difference in the response. Then we have resolution 3 designs in which the main effects are not confounded with each other, but they are confounded with two-factor interactions. So that means I know if I observe a difference whether it comes from A or B, but what I cannot be sure about is whether it's really because of the main effect of A or the interaction between A and B. There's some degree of confounding. And if you want to remove that confounding, then you go to a resolution 4, but then you have confounding with three-factor interactions and things like that. So the higher the resolution that you need for your study, the higher the sample size is going to be required. And again, it doesn't matter how many times you replicate your study, how many times you make observations given the same design. What's important is the design. And if you have a lot of data with a bad design, then by the time you analyze the data, you are not going to be able to tell whether one factor is causing the effect in the response or whether it's the other one, because it's confounded. So it's very important that you just don't go out and start collecting data. It's very important that you sit down and think about what effects are you interested in, and then make a plan to study those effects specifically, because not every design is going to allow you to answer those questions. So general principles, I'm not going to cover them, are random assignments of individuals to the treatments, replication of your experiment, blocking orthogonality. So the specific way in which all these combinations are laid out in the table, they're made in a certain way such that the effects are orthogonal, and balance between observations. So you want to have the same number of observations per combination of treatments. I'm not going to cover this in detail. It's just general principles to know about. And so I think the idea is you have to think very carefully about what effects you want to study, and then choose the design accordingly, not the other way around. It's all about finding a compromise between the number of runs that you can afford and the number of effects that you want to study. That's what determines the resolution of your study, and it's all about the balance. Now, in practice, very, very rarely you're going to be interested in interactions between more than two factors, because they're very, very hard to interpret, and they're very likely to be just spurious, to be just random coincidence that you see something. There are, of course, standard designs to apply in typical cases, and there's plenty of software tools to help you make a study, a design for a study. You have some links by the end of the slides. So what I'm saying is there are tools to help you solve this problem. It's not that you have to do all the math yourself. And as an example, let's say that if you want to study 5 factors and they are binary, if you want a resolution 3 design, that is, you want to study the main effects and you don't care if there is confounding with two-factor interactions, or you assume because of the knowledge of your problem that those interactions don't exist, then what this says is there's a certain design and you're going to need to run 8 observations. If you are interested, on the other hand, in a resolution 5 design, so that you do care about two-factor interactions, then you're going to need 16 runs. And there is a specific table. This is one specific table of length 16. This is one specific table of length 8. It will be about choosing the one that you want and going ahead and make the observations. But which specific observations, it's already designed for you. And you know that it's going to allow you to minimize confounding to the level that you require it to be minimized. And there's something else called optimal designs. I'm not going to stop in there. The idea is that sometimes these standard designs, like in this slide, they are not useful for you because of whatever reason. Because of the number of factors and levels, maybe you have a very specific combination that there's no standard design for, or maybe you are interested in some effects but not in others. So for example, you might be interested in the interaction between A and B and C, but maybe not the one between A and C. So there are certain algorithms to make these optimal designs, tailored to your specific needs. And it's just an algorithm that makes the table for you. And in the end, it's about the same. You have factor A, B, and C, and it's about minimizing the number of runs that you're going to be required to run in order to estimate whatever is it that you want to estimate. And yeah, I can skip this. One final couple of mentions because we are already reaching the time. Just the difference between an experiment and a quasi-experiment. If once you have the variables, you have the design table, you know what you're going to measure and how, which specific combinations you're going to measure, etc., then you have to start assigning subjects to those treatments. So you have the table, and now you have to start assigning people or whatever is it that you're interested in to each of those rows in the table, to each of those treatments. How you do it is going to determine whether you have a true experiment or a quasi-experiment. If this assignment of subjects to treatments is random, it's completely random, we have what we call a true experiment. And the thing is that we expect that if we are missing some variables, we have some third variable problems. So let's say that because of whatever reason, there are certain people that are different from others. You can think, for example, about the kidney stone example that we had in the last lecture. If there is any difference in there, then by doing the assignment randomly, we expect the effect of that difference to balance out across the different factors that we have in the experiment. So we are expected to minimize the effect of this third variable that we are not accounting for. All this by randomly assigning subjects to treatments. So it's going to give us a higher degree of internal validity because we are minimizing the possible effect of things that we don't know about. If there is no random assignment, we have a quasi-experiment. And this was the case of the kidney stone. If we do not make the decision of which patients go to which treatment, but still we can measure the size of the kidney stone. This would be a quasi-experiment. And the point would be we are not making sure that whatever effect of the size of the kidney stone is going to be balanced out across the different factors of our experiment. And then a non-experiment is one in which you have absolutely no control. You're just observing something. So everyone aims for true experiments, and that requires random assignment of subjects to treatments. The reason, again, is that you are expected to balance out possible effects of other third variables across your experiment. We have something called pseudo-replication. I'm going to skip it in the interest of time. Just give it a read. And there's plenty of threats to internal validity. So apart from the experimental design, there's plenty of things that can go wrong. So I suggest you go to Wikipedia. There's a link in the end and just give it a look, see what other things we care about when we are designing a study. And that was it. So summing up, we talked today about the levels of measurement and how to build a scale to quantify some concept of interest that is very difficult to quantify and is very subjective. We talked about populations and samples and the idea of random sample, a random error, what the random error comes from, factors and their effects, and how to make a specific study design given whatever effects we are interested in. That's what we covered today. And there's some links for further reading if you want. The first one is a book that is completely free online. I suggest you just go there and take a quick look, see the basic topics that we're covering in the course. If you're looking for more advanced topics on the design of experiments, there's this excellent book by Montgomery. Here you have a link or a list of keywords that you might be interested in taking a look at. And finally, as I said, go to Wikipedia and look for threats to internal validity, cognitive biases, and all these different things that we should keep in our minds when we are designing a data-driven study, especially if, again, you're working with people or something that it's very likely to have a very high degree of variance and unexplained variability in the responses. And finally, if you want to start looking into how to make your own designs, your own study designs, fractional, factorial, optimal, and all these things, Here are some software packages that you can use. JMP is one that I used a lot. R is also one that I used basically every day. But since this course is in Python, you can take a look at this package that is going to allow you to create study designs given whatever constraints you have, full factorials and that kind of thing. And that was the lecture for today. I don't think we have anything else. Let me take a quick look at the questions. There's nothing. I will post the recording of the lecture in a few minutes whenever I have it. And just to mention, there was a question: will we be allowed to create our own group for the assignments, or are we randomly assigned? Probably you are going to be able to make it yourself, but we have to be quick. Yeah, in principle, it's fine. And if anyone doesn't have a partner by some date, we will just do it randomly. And I'm also thinking about changing how we do these live lectures because I would like to have more interaction. So maybe what we do is have a regular meeting in which everyone can just unmute yourself and ask a question rather than this intricate Q&A queue that we have to go and post a question and accept the question, and it's a little bit messy. So let me take a look and see if we can do it in a better way. Again, the full schedule of the course is going to be posted today. Don't worry because you don't have to submit anything this week or the coming week, so don't worry about it. And there's going to be a lab for you guys probably tomorrow, but this one does not count any points to the grade. It's just a refresher of Python. So I think that was it. Let me take another quick look at the questions. There's nothing, so I think we can end here. Thank you for staying. Again, I will post the recording in a minute, and see you next week. I will update also Brightspace. The coming lecture is going to be on Wednesday. There's no lecture on Monday. Okay, see you all next week.